Hello, everybody. Welcome to the AFT webinar for Wednesday, March 4th. I'm going to be your presenter, Nick Vastine. I'm a business applications engineer here at Applied Flood Technology. Before we get started, let's try to make sure that everything's running as intended. So if you guys can, populate the chat, let me know if you can hear me. I'd greatly appreciate it. Just as a follow-up, let's make sure anyone can hear me. Can everyone hear me all right? All right, well, it looks like everyone can hear me, hopefully. We'll get this started. We'll get this on a roll. So today we're going to be talking about how to avoid 3 big operating problems with AFT Fathom. Hopefully everyone's here in the right place. They signed up for the right webinar, but if not, we're more than happy to have you here. So with AFT Fathom, we're looking at incompressible flow. Hopefully you guys are familiar. Hopefully you guys are all customers, and we all greatly appreciate your business. And in this case, the 3 big operating problems fall into 3 categories. So first, we'll go over kind of a loose agenda. We'll see the different topics we want to start off with. So to start off, we're going to look at operating outside of a pump's preferred operating region. We'll get into how a preferred operating region is defined, and we'll also go a little bit into what the best efficiency point is and what the importance of having a BEP proximity is. So first, we'll go over what the best efficiency point is. We'll talk about some of the different operating cases we might see, why a pump might operate away from BEP and what can cause those deviations, as well as some potential ways we can correct them. We'll look through a theoretical example where our pump is undersized, and we'll compare kind of the implications if our pump was instead oversized. So that'll be a good general conceptual idea that we can take and apply to any models that you guys may be having trouble with. The next topic that we wanted to look at is cavitation. For pumps, this primarily comes in the form of net positive suction head, or NPSH. We'll look at some potential causes as well as some resolutions that we can try to apply to alleviate any cavitation that might be happening in a system. We'll also have a little brief aside about valve cavitation, which isn't something that Fathom will really consider, but it's something that I found interesting and something that you can definitely consider in your model, despite not being able to show it with quantifiable data in Fathom necessarily. Finally, we'll take a look at control valve failure. We'll talk a little bit about when you should be applying control valves, when you shouldn't be applying control valves. When control valves do fail, what's their criteria for failure? What's the state that they can go into when they do fail? And then we'll also talk a little bit about always control, how that can be helpful in both troubleshooting or using control valves to size things like valves and whatnot. So to start off, we're going to start by looking at the best efficiency point. Our first question is, generally we'll be given a manufacturer curve for a pump. In this case, we have a range of diameters ranging from 10 down to 6. And so these diagrams are really good for compacting a whole lot of information in one place, but it's not necessarily really easy to determine where that best efficiency point will be. For our 10-inch impeller, we can see that our efficiencies grow from 31 to 36 all the way up to 58.7. So on the 10-inch curve, it's really easy to determine the best efficiency point. We can just look at where this 58.7 is, draw a line straight down, it'll be around 245 or so. In our case, our pump that we purchased is a 9-inch. So in Fathom, you can't really import an image like this, but it's really easy to kind of digitize these plots, get points for not only your performance curve, which is going to drive all of your flow in your model, but also account for either efficiency or your power. So we can turn this plot, which has a lot more information than we need, into a nice table that's easy for Fathom to interpret. And this was done with just a web plot digitizer. You can also do it by eye. As long as you're close, the data fitting that Fathom's going to apply is going to be more than enough to get you all the way and approximate this curve. So notice that I've specified both efficiency and power. This will come up in a moment when we talk about how we're inputting into Fathom. But right now, we'll just focus on this efficiency. And even more specifically, I want to make note of these 2 points. It's very important to try to get as close to this best efficiency point and kind of refine where that inflection point will be, or I guess maximum point will be. And the closer we can get to that, the more accurate our best efficiency point will be. So now we have our table, which we stripped from our manufacturer curve. Hopefully it's correct. Now we can take that curve and we can input it into Fathom. So here we have a pretty simple model. This will go through a lot of the concepts that I want to touch on about why you can deviate from BEP. So we'll just get a little bit of familiarity with this model in general. So if you're using a pump, generally you have something at A and you want to get it to B, usually by overcoming pressure loss, whether that pressure loss comes in the form of static pressure, which it does in this case. So currently we started atmospheric and then we climb up to 125 PSI. So this pump is going to supply that pressure. We also have to overcome any losses we might see in these pipes, as well as from this valve. So we take a look at the pump itself. Generally, when you start your model, it will start in this sizing mode. After you size your pump and you figure out what candidate that you can pull that manufacturer data, and now you can implement a pump curve, where this is going to be, much more valuable when you start playing with scenarios, seeing how it'll deviate along this curve for different operating conditions. From the pump curve, we can use the enter curve data and look at this convenience. So all of our flow data is in, all of our head data is in, as well as all of our efficiency. We can generate curve fits, so we can see that now instead of a collection of points on our pump curve, so instead of trying to interpret this for our efficiency curve, now we can instead look at this nice clean curve. And evidently, we can see our best efficiency point. One thing to note with pump data just in general is if you specify, let's say you put a control valve and you specify a flow control valve at 25 gallons per minute, it's unlikely that this pump is going to read exactly 375. That's just because it's not pulling these data points exactly. It's fitting a curve to them, and so it'll exist very close to your input, but it has to meet this curve, so that way it's meeting all of these different points. So we can see one for the performance curve. We can also see one for this efficiency curve. This is why it's important to have these 2 points around the 58% efficiency, just so that way you know where that best efficiency is. Easy to get close, and it's hard to get even closer. Right? We can also take our composite graph. This is easy enough to print, or if you want to customize it, those are some options. But in our case, we're mostly concerned with specifying the pump, specifying efficiency. Some other things that we can consider in the pump properties, and this will pertain more when we get into operating regions, is we can also specify those operating regions. And we'll get into that a little bit more when I start defining the preferred operating region and the allowable operating region. So if we go back to our presentation, we have our table. It's all input into Fathom. And now we've produced this performance curve. And now it's really easy to see that here's our BEP. We can call that our BEP flow rate. And that's going to be important because this is kind of the measure we're going to use for all of our deviation, whether it's in our preferred operating region or extends out to our allowable operating region. So why is BEP important? Why should we even consider it in the first place instead of just buying a pump that's going to run? We can meet our pressure spec, we can meet our flow rate spec. Well, BEP is important because one, it's maximizing the efficiency of the pump. Rather than dumping energy into the pump that's being wasted, all of it's going into your fluid effectively. So this is minimizing all of your wasted energy. Once we start to deviate from BEP, that wasted energy starts to contribute to other things like vibration or heat energy, where heat energy can, heat up your fluid, heating up your fluid, also heating up your pump casing. As your pump casing expands, That can cause issues with alignment and can lead to excess wear and tear, generally things that you don't want your pump to see. So if instead of operating away from BEP, we operate near BEP, we can avoid some issues like pump seizure, we can avoid low flow cavitation, recirculation. As that fluid in the pump recirculates, it can just get more and more energy put into it. That can increase the temperature, again, expanding the casing, causing potential alignment issues. As you move towards the right of the curve, you'll see your NPSHR increase, which can lead to cavitation. And in general, you'll just see excess wear and tear. So operating at BEP is essentially the pump's utopia. It's where it wants to operate. And so during the design phase, it's especially important to consider. So what if you're still not convinced about the importance of BEP? So there's actually standards in place from ANSI and the Hydraulic Institute. I put an asterisk on this because it's changed a bit recently, but this is kind of my rule of thumb. Generally, these will change based on pump specific speed, whether it's an axial pump or more of a radial pump. But in general, my rule of thumb is that your preferred operating region is about 80 to 110% of that BEP flow. So if we had a BEP of 100, we can go up to 110 gallons per minute or down to 80 gallons per minute. And for a visual perspective, that's kind of this range. So even though we have information for this entire pump curve, really we should only be thinking about, does this part of the curve line up with what we need it to do? The next step up from the preferred operating region is the allowable operating region. That ranges down from 50% and 115%. So that would be 50 gallons per minute and 115 gallons per minute in our simple example. Visually, that looks a bit like this. So one thing to notice is you can see the wide expanse that we gain from going from preferred to allowable, but we only gain very little amount on the upper end. The reason for that is you can imagine a vibration curve for a pump. So let's say you have vibration on your y-axis and you have Q on your x-axis. Essentially what it'll look like is it'll increase a little bit. It'll come down where your lowest point is BEP, and then it'll sharply ramp up. So as you move to the right of BEP, this is kind of the region that you're seeing, where that vibration can become overwhelming and you're losing a lot of energy because you're not operating at that pump utopia. So now we understand the importance of BEP. And if you're doing your job correctly and you're trying to consider all these things in your design, you should be picking a pump that's operating very close to BEP to meet your flow rate and your pressure spec. But there can be some reason that your pump is deviating from BEP, especially in the design phase. So let's say you put your pump that you designed and you build it into your system. You could have initially missized your pump. So potentially you were overzealous about your safety margins. Let's say you estimated your friction factor as 1.5 because you wanted to account for aging, as that thing is going to increase in roughness. Your loss assumptions could have been much higher, so you could have used handbook data, which should be conservative because it's much better to oversize that pump than to undersize it. So those are things to consider in that initial missizing of questioning those assumptions. There can also be unaccounted for changes to your system that might cause a deviation from BEP. So this can include things like changing fluid conditions. So if your fluid is heating up, it's going to be a bit easier to pump. There won't be as much resistance. And especially if it's a viscous fluid, as you heat up a viscous fluid, it becomes less viscous, so it'll flow a lot easier. So if your temperature drops down and it becomes more viscous, your pump might begin to struggle. It might not operate at that point that you intended it to. Another thing to consider is if your system's getting older, so your components could start breaking down, though that's kind of unlikely. You could see potential issues like scaling on your piping, where you're closing up that internal diameter, and roughness could also, gradually increase depending on the circumstance. Another thing to consider is changing component conditions. So this can especially be an issue if you have manual valves rather than control valves, and they have to be set to a kind of a precise level. So let's say that you have an operator, and rather than it being a full open or a full closed valve, you have to try to finesse it to about 50%. And so, especially with some valves, based on the characteristic curve, what you think is 50% may actually be 60%. And so that can cause difficulties, and that can also run into problems if, again, you're running into these assumptions. One other thing to consider is variable inputs. So this could be changing inlet pressure. Let's say you had a pumping system where you're running from a body of water. If you have different levels of water, that can change, the static pressure that it has to overcome. And it can also affect the elevation that it might have to pump up to. So these are all things to consider. And it's generally expensive to try to field test all these suspicions. So it could be a bunch of different things. It could be a combination of all these factors. It wouldn't be too helpful to go out and start playing around with valves, especially if, it's easy to break down and might cause problems down the line. But it's more than easy enough to try to test them and experiment at the comfort of your desk with AFT Fathom. And so that's kind of what we're going to do today. We're going to look through a theoretical example. In this case, we have a pump, the same pump curve that we defined initially. Currently, it's misbehaving. It's producing less flow than we want, and it's outside of our preferred operating region. We want it to operate here, which is about 210, but really it's operating at around 150 gallons per minute. So the first assumption we want to make is that the pump's not defective. This can be important because a lot of the changes that we're going to make are going to be to the system. And so if the pump was the issue, then all of our changes to the system may be irrelevant, or they may be covering the problem. So that's one thing to consider. And a lot of the suspects that we see are a lot of those causes of deviation we might see. So for component losses, we can take a look at valve position. We can look at if aging is causing the problem, what kind of roughness would we see, or what kind of roughness would we need to reduce the flow down to that 150 gallons per minute. We could also test how much scaling there would need to be, and maybe if there was a change in our downstream pressure, how could that impact our system curve to bring our flow back. So now we'll go back to that model, where first we have our base scenario running at BEP. And so in our pump summary, we can see we're operating at 203.9, 96% of BEP. That's pretty good, quite impressive. We also see our NPSHA, that'll come in handy later, and it also provides our BEP flow rate automatically. So based on our current design, we're pretty much set. Our BEP was great. Now we can start trying to deviate and see what would cause a drop from 203 gallons per minute down to 150. So a little peek behind the curtain. If we wanted to do valve position, this is a pretty simple curve that I made. Essentially, this valve is assuming that it's a globe valve. It's 52.5% open, which gives us a CV of 50. We can take a look at our graph. So this is where characteristic curves are important, especially if it's a manual operator trying to finesse a valve. Closing it an additional 10% can drop the flow very significantly compared to, this initial closure. So that's something to be aware of. Not all valves are going to be linear. So we can take a look at the valve. The valve is the easiest one to try and figure out what CV would cause a drop to 150 gallons per minute. This is kind of one of the more unique applications of control valves. You can use control valves to size traditional valves. So in this case, we have our control valve set to 150 gallons per minute. That's our flow rate that we measured in the field, and we're trying to figure out why we're hitting that instead of our 200 goal. We can go to our output, take a look at our valve summary, and here's the CV that valve would need to be at. So at 26.59, we can go back to our valve, back to our characteristic curve, and in the ballpark of about 37%. So we drop down from 52.5% to 37%. That's not terribly unreasonable. If we're looking at a globe valve, we can see kind of fine control, so it's good that there's a wide range of CV for a pretty small change in open percent. If we give this a run, we can take a look at our output, where now we see this warning, where before we did not. So junction 1's BEP is below the preferred operating region. So because we're at 70%, we're below my 80% threshold, and that warrants a warning. We can also see in our pump summary that we're at 71.25%. And our valve is operating as intended with our 150 gallon per minute flow. So the valve's pretty easy. That's a very viable option at this point in terms of what could be causing that additional loss. The next variable we want to look at is scaling. So here was a test that I ran already. You can see that junction 1's BEP is below our preferred operating range. It's also causing an error that our static pressure is lower than our vapor pressure. So this is another variation of the cavitation error. This will occur in pipes where the static pressure is below our vapor pressure, indicating that the fluid's vaporizing. And Fathom will still give you results, but it's important to be aware of these warnings and making sure that your results are good before you start moving into the next phase of design or anything like that. For scaling, this is where it starts to become a bit more tedious to do hand iterations. So with each pipe, we have this specification, the internal diameter reduction in scaling. I already went through the math and found that it was 29.6% scaled. So for a 3-inch pipe, we can reduce that by 30%, and that would cause the equivalent pressure drop, or the additional pressure drop, to cause our flow rate to drop 50 gallons per minute. And so that can be done by hand, or if you have the goal seeking control module, that's where it can get really convenient, where you can set these pipes, you can change your variable parameter to internal diameter reduction, and you can deviate for you until it meets this goal, which in our case is this volumetric flow rate of 150 gallons per minute. So that's one convenience of goal seeking control. If you have it, there's a lot of different applications you can use it for. We'll have an upcoming webinar all about goal seeking control and all the cool stuff that you can do with it. But in this case, it's good for troubleshooting a system where we want to vary these parameters and we want to vary them automatically instead of with hand iterations. So our scaling, we went from 0% to 29%. That's quite the amount. Our valve, we dropped from 52.5% to 37%, which is a bit more reasonable. We can take a look at roughness as well. So in my testing, our roughness turned out to be 0.4185 inches. Now, roughness is one of those things, personally for me, that it's hard to get kind of a scale. So 0.4185 inches, oh yeah, that sounds like a good number. But if we compare to the kind of user default for steel, kind of the accepted value, you can see that it drops down to 0.0018. So that's quite the jump from 0.0018 up to 0.48. I imagine you're pumping through something like sandpaper at that point. I'm not quite sure, but it doesn't seem at this point that roughness would be something to consider. The final thing that we wanted to consider is downstream pressure. So this, rather than looking at kind of the variable resistance of frictional flow or through a component, now we're looking much more at the static. And we'll go into system curves and we'll look at what that looks like for each scenario. So in this case, we can run our GSC where we would vary this junction, again, trying to meet our goal. In our case, I already ran it here, transferred some results over. So originally this junction was at 125 PSI, and now it's increased by 23 PSI. So it may be reasonable and maybe not. Looking at this small of a system and being very theoretical about it, anything could cause that change. But again, it's something to consider if you're running into issues with your BEP. So the nice thing about Fathom is talking about system curves, we can also generate these system curves. We can do it pretty easily. So we run our model, we can go to the Graph Results tab. Here we can select our pump versus system. We can show our pump curve, and we can also show our preferred operating region. I like to specify my own flow rate just so I can get a wider expanse. We can generate. So here we can see our preferred operating region. It's very clear that our system curve is intersecting not within our preferred operating region. It's at 70%, so it's within that allowable region, but again, we could try to see if it's something that we can correct in our system so that the pump is approaching that BEP. Another cool thing, this is new to Fathom 11. So if you haven't installed that yet, that came out about 3 weeks ago. This is one of the new features that I'm pretty excited about, is you can generate multi-scenario graphs. So over here, I have my graph for my valve when we vary the valve closure, with roughness when we vary the roughness of the pipe, scaling, downstream pressure, and then we also have the BEP operation, or just our base scenario for reference. So we can go ahead and load that. We can select our different system curves. We could potentially select the pump curves for each, but because it's going to be the same pump in all the scenarios, we can just leave it in the base scenario. We can generate our graph. So this is where it gets interesting. So these dashed lines are our BEP operation. This blue dashed line is our starting system curve. We can see we did a good job staying within that preferred operating region. This dashed red line is our pump curve, and we can see that it's intersecting all of our system curves at this 150 gallon per minute. But we can see that our changes cause some pretty drastically different results. So scaling, roughness, and the valve closure, those are all changing kind of the frictional aspects, the pressure losses that are going to vary with flow. Whereas when we changed our downstream pressure, we can see that now our y-intercept is moving. So now, not only does it have to overcome that frictional change, it looks like it's overcoming pretty much the same frictional change. Now it has to overcome this increase in static pressure. And this is cool, so we can look at each one individually if we want. We can compare. And so this is a really easy tool to see, what are the operating conditions, especially if you're looking at designing a pump that will operate in multiple different scenarios, like winter and summer variable demand. This is a cool tool that you can use. And so with that, we can take a look at our results. So if we looked at our downstream valve CV, we can see that it closed down to 37%. This is pretty reasonable, I would think. Pipe roughness increased, almost 400%, or potentially 200%, we'll see. But this does not seem like a very reasonable option of why we would be seeing this deviation in BEP. Our scaling is a bit more significant also at 29.7%, and then our downstream pressure could also vary. So these are the kind of things that you want to be considering. You want to especially look at the system rather than just the pump when you're looking at what's my operating point, how do we move away from that? Or how did we move away from that? And here's another copy of our multi-scenario pump system curve where we can see that change in static pressure and our change in variable pressure, where you can consider that, it might have been a combination of these things, and that's where you can get really creative with creating different scenarios. So keep an eye out for an upcoming blog on these multi-scenario graphs that should be coming out probably around March 15th. So make sure you're signed up for the AFT newsletter. If you're not, feel free to give me a shout. I'll make sure that you're signed up and don't miss one. So we looked primarily at a circumstance where our pump was undersized. It wasn't producing enough flow. Now we're going to look at if it was oversized. So undersizing means that we underestimated our frictional losses. The losses seen by the system are much greater, forcing it to move to the left of BEP. Oversized is just the opposite. We overestimated it. We bought a pump that's too large. Now it's operating to the right of BEP. And so these losses can come from different places. So the valves might be closed. Oversized valves may be too open. We can look at temperature. And then we can also look at some static effects like change in elevation, or if our static pressure at our inlet and outlet were changing. And then finally, we can also look at component losses. That kind of folds into the frictional loss aspect. And so that's kind of the pump operation portion of this webinar. Kind of the importance of BEP, why you should consider the preferred operating region, some things to consider if you notice that your pump's deviating, and how you can test those things in Fathom from the comfort of your desk. And with that, we're going to start moving towards cavitation. So cavitation, hopefully everyone's familiar with it. It's the creation and subsequent collapse of a vapor pocket due to rapid changes in pressure. Great definition, killing it. So the one thing that I used to run into issues with cavitation is there wasn't really a theoretical understanding. There wasn't kind of the why these things happen. It was more of, oh, if your pump is cavitating, that's not good, you shouldn't do that. And you would really only think about it in NPSHA and NPSHR, which we'll get into. Cavitation is due primarily in centrifugal pumps because you're accelerating the fluid. So as that velocity increases, your static pressure decreases. That can decrease below your vapor pressure, causing the vapor bubble. And it's not the creation of the vapor bubble that's the issue, it's that collapse that's causing the problem. So as the high pressure around it punches back in, it punches a little hole, kind of like a donut, I guess, and that'll damage your surface. And so the way you may be able to see that your pump's cavitating in a system is you'll probably hear it. It won't sound like it's operating correctly. You'll probably see a lot of vibration, and then also it generally like sounds like gravel is going through your pump. So not really something that you want to happen. So with cavitation, how most engineers will think about it and approach the problem is looking at NPSHA versus NPSH, in this case 3, or more generally the required net positive suction head. So NPSHA is all about what pressure do we have at this certain point. Usually we apply it to pumps, but you can also look at other points in the system. And at the pump, there's really 4 big components that you have to consider. So the first one is the pressure that you're adding on. So if we imagine that positive suction head as a static head of fluid on top of your pump suction, any pressure that is hitting that pump can deviate or can increase and help to improve that allowable thing. We can also look at things like height or your static head. That can increase and decrease depending on where your pump is relative to that fluid. So if your pump is above your reservoir, that's going to be a negative head because now it has to overcome that additional pressure loss of, pumping up to the pump. So that's why it's always generally better to keep your pump as low as possible and you're getting as much head as you can, right off the bat. The next loss component is friction, which can come in the form of things like components and other frictional loss, whether that's from pipe diameter. And then finally, the last component is vapor pressure. One of the points that most confused me about NPSH in general was like, where does that vapor pressure component come into play? Originally, I thought it would be on the required side, but because NPSHR is regardless of what you're pumping through it, it makes sense to apply it to that available pump head and just discount it off the top. So there's no real point looking at NPSHA without looking at NPSHR. In this case, we're looking at a kind of more recent definition, or we're looking at NPSH3. So in a formal sense, this is the net positive suction head on the pump suction where your head is reduced by 3% at a given flow rate. So if your pump is pumping at 100 feet of head, as you decrease the head of fluid at the pump suction, once it reaches 97 feet of head, that's where you can mark your NPSH3. It's sort of to standardize how all of these different pump manufacturers were originally defining what's the required NPSH to avoid cavitation. And this is determined experimentally. It should be provided by your pump manufacturer. And so as long as our NPSHA is greater than our NPSH3, in this case, we shouldn't see cavitation, but I would be hesitant to, try to set them equal and try to save some money that way. So what does NPSH look like in Fathom? So we can go back to that pump curve where now instead of looking at the performance, the efficiency, and the power, now we're looking down at this NPSHR portion. So for our 9-inch impeller, we can use our plot digitizer again to pull some necessary head, and we can see how it grows pretty steadily, and then it starts to ramp up. And so remember with that preferred operating region and that allowable operating region, how we could go all the way down to 50% of BEP flow, but we could only go 15% above it. That's another contributing factor in addition to that vibration effect, is now you're much more likely to see cavitation. So we can take a look at our pump model again, where we have a nice scenario about adding NPSHR. We do that in the same place where we enter our curve data, where now we can fill this NPSHR in terms of feet. Generally, it's good to keep it in terms of feet because it doesn't matter what you're flowing through that pump. The only thing that matters is kind of the head that you're seeing, those feet of pressure. And so here's another place we can see with configuration data the importance of BEP. We can also specify it. In our case, if we wanted 210 to be our gallons per minute. And then here's where I was kind of touching on the rule of thumb preferred operating region. I user specified this as 80 and 110%, but if you have more information, if you know what your specific speed is for your pump, then you can let it determine it automatically. So the higher, the more axial, the lower, the more radial, I believe. And so that'll vary those ranges. And there's some other standards you can try to apply, and you can see how maybe it widens it, maybe it shortens it. And then from the allowable operating region, there's less standards involved. And so that's much more up to you, and you can specify that as well. But I would hope that after this webinar, you're really shooting to design within those preferred operating regions. So we have our NPSH in, we run our model, we can go to our pump summary, and we can see that our NPSHA is greater than our NPSHR, and we're not cavitating, which is great. Some other things that we could consider in this pump summary comes back to that idea of safety margin. It's not really responsible to run your NPSHA equal to your NPSHR, especially if you're making assumptions about friction or any of those other assumptions that we made when we were looking at pump operation. So if we go to output control, by clicking this spreadsheet with a pencil in the top left, in our output control display parameters, we can go to pumps, and we can use our nice filter to search for NPSH. So we can look at our absolute margin. So in this case, it would be the difference between 24 and 8. You can set things like design alerts. So if it goes below 10 feet, it can notify you, especially if you're playing around with different scenarios. You can also look at the ratio. So maybe you want a 1.2 ratio, especially if you're considering like high NPSHR pumps. So those are some different options you can use for your metrics. So let's look at what kind of error message we'll get if we run a pump when it's cavitating. The way we're going to do that is by adding some upstream losses. In this case, I added a valve with a K factor. This is one of the reasons that you never want to throttle your pump upstream, is because you're taking away from that NPSHA to try to control flow rate before you're adding all this pressure where it's safe to do so. So we can run it, take a look at our output, and we can see that our pump junction has insufficient NPSH. And it gives us our required and our available, so that can give us a ballpark of what kind of NPSH would we need to add to make sure we're not cavitating this pump. So here's where we can specify it in Fathom. The configuration data is where you're defining your preferred and allowable operating regions. So here's some things that we can consider for a cavitating pump. You see a lot of the same factors. A lot of these things have to do with the system itself rather than the pump itself. So if we look at like inlet head and pressure, well, if that drops down, that's already dropping our NPSHA. Upstream losses, that can come in the form of trying to throttle it upstream, which is not recommended. Or if there's a lot of bends and other kinks leading up to the pump, that can cause issues. And then other things to consider is like friction and aging. We can also look at elevation. That's that static change. So above the source, it'll hold down your NPSHA. And then fluid temperature, the hotter your fluid, the higher that vapor pressure is going to be, and it's going to be much more likely to cavitate. So how can we try to resolve these things? How can we try to treat them? Well, essentially, we just try to do the opposite. So if our inlet head pressure is too low, we can try to increase it. We can try to adjust the tank level if we're pulling from there. Our upstream losses, we can try to minimize that in our design. Maybe we could fit a larger diameter pipe so there's not as much frictional loss from just flowing through the diameter. We can also change our elevation. So this is a place where you could consider a vertical pump where the impeller is at the base of the pump. And so any flow coming in enters at the top, and you immediately gain the elevation of that pump down to the impeller. That, in addition to space savings, that can help if you have a cavitation issue. And finally, fluid temperature, you could consider cooling the fluid before pumping. This is probably much more rare. NPSH is probably much more significant in terms of elevation. But if you're looking at something very volatile like hydrocarbons, then it may be something to consider because that vapor pressure can be quite significant. One thing to note is that any of these resolutions can improve it as long as you're working on that side of the equation to make that number bigger. It'll help you achieve that margin that you're shooting for. So here's a short little aside about cavitation and valves. So in Fathom, when you represent a valve, it just represents a pressure loss. So you'll have your flow coming in. It'll decrease due to frictional losses. It encounters this loss, which could be an orifice, it could be a general component, it could be a valve, any number of things. It'll determine the loss through it based on the flow rate, and then it'll keep on flowing. In reality, especially with a valve, it can get more complicated than that. So not only is it reducing the pressure, drop in stagnation, you're also going to see a contraction. So if you imagine the valve as a very small hole that all of that flow has to pass through, we're going to see our static pressure drop. This comes from the balance of stagnation pressure equaling your static pressure and your dynamic pressure. So as your velocity goes up, your dynamic pressure goes up. As a consequence, that static pressure has to drop. And so it may even drop to the point that it's going below that vapor pressure and causing cavitation. You may be asking, why don't they have NPSHR for valves? Well, I don't think that the damage is nearly as significant, and I think that valves are not as expensive as pumps in most cases. And so I guess it's kind of like a issue you just don't really talk about. But it's important to be aware of it. Note if you spot cavitation in a valve in your system, or if you believe there might be, this is something to consider, but in no way will Fathom really indicate to you unless you're cavitating at this outlet of the valve. Then it'll be an issue because then you'd be cavitating in essentially this entire pipe. So that's cavitation in valves. Cavitation just in general, looking at NPSHA, NPSHR. Again, how do we look at the system instead of just looking at the problem area of the pump itself? So that brings us to our final topic, control valve failure. As an introduction, we'll just look at control valves in general. You've seen an example of how you can use a control valve creatively to size a valve. But there's also a lot of misapplications of control valves. And so these can occur, especially if you're trying to match your system to field measurements. A lot of the time we will see, I'll draw it for you. We will see a assigned flow, and then we'll see a pressure reducing valve. So that way we get the flow rate that we measured, and we can also get the pressure that we measured. That's kind of like over defining your system, and that now Fathom Solver doesn't really have anything to solve because you've over defined the system. And so that's one use of control valves that you shouldn't, try to be using. But control valves are a great tool. They make everyone's job easier until they don't, which is unfortunate, especially when they're failing. And in Fathom, we have 4 big control valves. One is less about control. It's kind of a workaround, and we'll get into that a little bit. But here's the general control valve property window. We can see our models. We have our 4 types. So we have pressure reducing, pressure sustaining, flow control, and then we also have our constant pressure drop, and we have our set point for each one. And then we also have our action if set point is not achievable. So that's kind of our condition for, well, this control valve is failing, what should it do? And we'll get into that after we look at our different types of control valves. So the first type is pressure reducing. In this case, we're trying to set the pressure immediately downstream of the valve. Pressure sustaining is the opposite, where now the set point is the upstream pressure. Our flow control valve controls flow, right? And so that'll seek to limit flow by increasing pressure drop. And then finally, we have the constant pressure drop, which applies a constant pressure drop. Who would have thought? So if we look at failure, there's a few different criteria for failure. So for pressure reducing, we can see that if there's insufficient upstream pressure or excessive downstream pressure, let's take this kind of piece by piece. So if there's insufficient upstream pressure, we'd expect our valve to open all the way. because it has no pressure to remove to reach that set point. And if our downstream pressure is exceeding our set point, well, we can close off the valve because we're already all set on all the pressure that we need. The opposite is true for pressure sustaining. So if there's insufficient upstream pressure, it'll close because it's trying to maximize the pressure that it's seeing. And if there's excessive downstream pressure, it'll open up all the way, because any upstream pressure, by closing the valve, you're increasing that upstream pressure more than you already need to. Those are the two confusing ones. We'll go a little bit into that in looking at kind of the actions that we'll see. Flow control valves are much more intuitive. So if there's insufficient flow, if your valve is fully open and you're still not seeing the flow rate that you're controlling to, it'll fail open because it has nothing to control. It has no pressure loss that can correct the overpressure it's seeing. And then finally, there's constant pressure drop. Technically in Fathom, I don't think it has a criteria for failure, so it won't open or close. It'll always apply that constant pressure drop. One scenario that I thought of was if your pressure drop is greater than your pressure at the valve inlet. So let's say you have a 10 PSI drop and your valve inlet is 5 PSI. Well, you're going to get negative 5 PSI. That should kind of be a red flag for any engineer seeing a negative absolute pressure, especially in those kind of cases. Or it might cause it to cavitate, and that could be a problem too. So now we can look at failure states. This is kind of what I alluded to with opening fully and closing fully. In the case of a flow control valve, it's very simple. If there's not enough pressure that you can reduce the pressure to control the flow, just open up all the way, let as much flow as you can through. Another thing to notice is this always control check. We'll go into that a little bit more as we work through this example, but note that this is also where it is activating and deactivating. So now let's take a look at our model. And so here's our base scenario. We have a pump defined with a pump curve. We have two control valves, which are set to 100 gallons per minute each. And we have this throttling valve, which is currently all the way open. It's considered lossless. And so if we run it, and we check our valve summary, we can see that we're getting our desired flow rate through each one. So this is great. We don't really have a problem. Our control valve isn't failing. There's no issue here. Now let's start trying to throttle the loss. So again, this pressure drop could be caused by a number of things. Maybe you measured it and you saw, oh, from this pipe to this pipe, we see a 10 PSI. We don't know why that drop is, but we know that it exists. We can account for that in our model. That's a good use of our constant pressure drop control valve. And so in this case, we're going to drop it by 10 PSI, and we're going to see what happens to our system. So now what we see is two critical warnings. So these are a step up from just normal warnings, because now your system's being fundamentally changed by the software. In no way would you see these results with how you've set up your system. Or you would never see these results in your physical system, I should say. So we can see that flow control valve could not control flow. At junction 6 and at junction 7, so our two flow control valves, pressure was added to achieve control flow. See valve summary for more information. So now let's check out the valve summary. We can see that both of our valves failed, and we have to add pressure. We have to add 2.5 PSI in case 6 and about 4.5 in case 7. So why are we still meeting this volumetric flow rate? So this is where that always control checkbox comes in. If that checkbox is checked, well, no matter what, regardless if it can control or it can't, it's going to try to add pressure until it meets that flow rate. And so that's why you see things like, oh, I got a negative pressure drop across my valve. Looks like it's adding pressure. And so that should be a red flag in your mind also. So the next step in troubleshooting, we know that our valves are failed. We can try to see why they're failing. The best way to do that is by manually opening each valve. So remember back to our failure state. So if a control valve doesn't have enough pressure upstream, it can't reasonably reduce any pressure to reduce the flow. So in this case, if we unchecked always control, that would be one effect, or we can manually open it. So by using special conditions in the optional tab, we can set to fully open. And that means that the valve is not trying to control at all. It doesn't matter what the set point is. And if we set it to fully open, another thing we can do is set the loss that it's seeing. So currently we're set to lossless. That's just for example purposes. But if you have an actual control valve with manufacturer data, here's where you can specify that loss. So when it does fail open, you can still account for the loss, even if it's reasonably failed open. In our case, we'll leave it as none, and we'll leave our optional as fully open. And we've opened up both flow control valves. Now we can run it, check out our output. We can see we don't have those warnings anymore because the valves aren't trying to control, so it doesn't matter if they can't. And now we can take a look at our valve summary. And so this is where it gets interesting, because we can see that one of our flow control valves is at 103. And remember, our set point was 100. The other flow control valve failed reasonably because it doesn't have enough flow above 100 that it can take away some pressure to bring that flow down. So the question is, like, what gives? Why is this flow, able to be controlled, but when we ran both control valves, they failed? So the issue with that is because both of them were always controlling, you can see that now you would assume some flow rate through here. You're also assuming some flow rate through here. The additional flow rate through here probably causes a pressure drop that permeates to here, and then you get insufficient flow at both of them because they're all assigning that flow at the same time. One way we can remedy that is to avoid using always control. So instead of trying to add pressure to the system, it recognizes when it should fail, and then it fails accordingly. So always control, never fail. It's very useful, but it's something to be very aware of when you're looking at a system. And if that warning comes up, you should be, on top of it, trying to understand it. So in this case, I've unchecked always control for both control valves. We can go ahead and run our model. Now in this case, we can see that our flow control valve could not flow at junction 7, but our flow control valve at junction 6 could. So junction 6, that was the 103 gallons per minute, still set to open, it's still able to control, whereas our flow control valve 7 failed open. And so that's something that you can work through and try to understand of the importance of always control, especially if you're sizing the system or if you're trying to determine valve sizings, that kind of thing. And then also to understand the implications of always control and how they can fail each other. One thing I do want to note that's interesting about, especially with control valves in parallel, is how it decides which one should fail and which one should stay open, or kind of the order of operations. So essentially, Fathom will run the simulation. It'll use always control just as the first iteration because it's trying to assume that both valves are going to control. Both of them in this case failed. So if we go back to this one, we can see how both flow control valves failed. Imagine this is the first iteration. We can see that this control valve has the greater pressure addition that it would have to contribute. And because of that, that means it's more failed than the other one, if that makes sense. So it marks this first valve for failure. It'll fail it open, and then it'll run it again, assuming that the valve can control, except for the valve that we've set as failed. In that case, if it failed again, then both of them failed. However, in our case, where we changed our failure default, only the offender valve failed, and this one was still able to control. So that's just a little tidbit about parallel CV failure. And that kind of wraps up the modeling aspects. So now if we go back to our presentation, let's take a look at our summary. So failure conditions, highly dependent on type of control valve, especially when you're looking at excessive downstream pressure or insufficient upstream pressure. Whether it opens or closes depends on the valve, or if it closes at all in the case of a constant pressure drop. Always control is helpful, especially if you're doing valve sizing and you need to figure out how much pressure you would need, but it can also be a pain, causing valves that wouldn't fail otherwise to fail. You can manually force your valve open. That's a good way to check if your set point is reasonable, especially in the sense of flow control valves. If it's all the way open and you're seeing 50 gallons per minute and your set point's 100, clearly that control valve can't do anything to help. And then also try to be considerate of how control valves in parallel are dealing with failure. And that's why it's good to, create different scenarios, play around with it, see how always control impacts your scenario. So that wraps up the control valve segment. So now we've gone through all three parts. We've looked at pumps and BEP, how you can deviate from that BEP point, whether it's to the right or to the left, depending on if you oversized or undersized your, frictional loss estimation. We looked at cavitation, and we also looked at control valves. So as a summary, see that BEP is incredibly important, so much so that they've created standards, and these standards even vary for different specific seeds of pumps. It's important to consider BEP in all of your different scenarios. That's where multi-scenario graphing can definitely come in handy. And if you have a physical system that you're trying to model, deviations from BEP can come from all kinds of sources. You can manually iterate, or you can use GSC, which is essentially solver in Excel, to avoid that manual iteration and get to the point a lot faster. Looking at cavitation, in the pump sense, it's always a consequence of NPSH deficit. And so that's where you can try to incorporate things like your NPSH margin or your NPSH ratio. And you can set design alerts for that. That can help alarm you if you're seeing an issue. But also kind of the resolutions, how all those things apply to try to improve your NPSHA. Finally, looking at control valves, largely dependent on the type of control valve, and understanding why a valve is failing, what triggers it to fail, how one valve failing can affect another valve, whether it succeeds or fails. And then also looking at always control. Because always control is a default, it's kind of important to be aware of, especially when you see critical warnings like that. And so I think that just about wraps it up. I'm not sure if we have much time for questions, but if there are any remaining questions, please feel free to send me an email. I'll do my best to try to answer them. If you want a copy of the slides, I'm not sure if we'll do that, but we'll also send out a link to the recording once it's posted up on YouTube. So if you learned anything, feel free to share it with your friends. Hopefully it was a good use of your hour. And just thank everyone for attending.